So let's look at a transformation on, let's say, -2 raised to x plus 1 plus 4. So we want to graph this function using transformations, and then we'll look at another application. And then we move on to log functions. So what is the base function used for, that I used to create this function? Exactly, indeed. 2 to the x is the base function. Excellent. First transformation in order of operations, please. First transformation in order of operations.
Parentheses and an exponent. That's what it's. Order of operations, right?
Yes.
So it'd be that plus 1.
Yes. 2 to x plus 1. What does this do to the base function? When I change what into what? What is the difference? What did I change?
You're increasing x.
I changed x into x plus 1. What happens every time I change x into x plus 1 for any function?
Do you go to
Exactly.
the left?
Exactly.
The left one?
Exactly.
I couldn't remember if that was opposite.
Indeed. Left one. Next transformation, please. Next transformation, number 2, will be on number 1. In order of operations.
Multiply would be next, right?
Very good. What does this do to this one? And what am I changing? Remember, that's the bottom line.
You're changing y.
Correct. So then, exactly. Reflect with respect to the, say it again. Tiffany, I think you said it. No, that would be x into negative x, right? X into negative x. X into negative x is with respect to the y-axis. But we are changing y.
So that's with respect to the x-axis.
Very good. Awesome. And number 3, -2 to x plus 1 plus 4. What does number 3 do to number 2? Very good. So this is a very good review for Wednesday, right?
Slightly painful. I hurt my head.
Okay.
It's like, I know this, but
How do I graph 2 to the x?
we have it. It's like
Very good. It's increasing on all its domain. So this is 2 to the x. And what is this reference point?
0, 1.
Excellent. Good. Now you told me to shift this graph left 1. Please give me my reference point where it's going and dictate where it's going.
-1, 1.
Excellent. -1, 1. So here is my new graph. So this is the graph of 2 to x plus 1. What did you say to me to do next? You said, yes, give me the reference point, which is here, -1, -1. Give me the reference point. It's -1, 1. I'm sorry.
-1, -1?
Correct. So this is it. So this is -2 to x plus 1. And then you told me to do what to this?
Move it up.
Good. So this is the reference point. Let's stop for a moment.
Sorry.
No, you're correct. Let's stop for a moment and identify the horizontal asymptote for all these 3 functions.
Y equals 0.
Perfect. When I shift a function with a horizontal asymptote up or down, what do I have to shift first? Say it again. What do I have to shift first when I shift the graph with a horizontal asymptote? So you told me to shift this graph up 4. What do I have to shift first?
X. The horizontal.
Absolutely.
Because you're going to have a new horizontal asymptote.
Where will it be the new one? Excellent.
Y equals 4?
Exactly. 1, 2, 3, 4.
Okay, that makes sense.
Y equals 4 is the new horizontal asymptote. Now please tell me, where do I move this point?
-1, 3.
Excellent. Very good. Well done. So this is the graph of -2 to x plus 1 plus 4.
I cannot graph and do that at the same time.
Is it clear?
Yeah.
Now, if I, we're going to get to that in a minute. So if I shift the function left and right, if I shift the function with a vertical asymptote, what do I have to shift first? The vertical asymptote, yeah. So here there was no need because all these three functions have the same horizontal asymptote. But once I shift the pink graph up 4, I have to shift the horizontal asymptote first. Any questions?
I'm drawing that real quick, I promise.
Yes.
I just can't draw and answer the question at the same time like that. Not a good multitask.
Another application for exponential functions is the compound formula. Interest compounded n times per year. Interest compounded n times per year. I didn't mean to put 2 e's in there, sorry. I'm gonna per year. And the other formula is for continuous compound interest, or continuous compounded interest.
Let's say n times per year.
N, lowercase n, n times per year. You do not have to memorize these formulas, they will be given to you. So interest compounded n times per year, or it can be continuously compounded interest. Here they are. P equals A1 plus R over n raised to nt. I'll explain each and every piece.
Is this still less than 4.1?
Still 4.1. And the other one, AE to RT.
Is one of them the first one, the second one?
Obviously, it's n times, so it has n. If this one doesn't have n, it must be
continuous.
exactly.
Okay.
Yes. Very good remark. So n times per year is the first. But now let's see what all these letters mean, because otherwise it doesn't make any sense. P is the principal. What is the principal? I deposit money at the bank or I take a loan. A, accumulated value. So if I borrow $100 from you at a certain interest, if I borrow $100 from you at a certain interest, I will have to give you back A, the accumulated amount, in 5 years. I cannot, you're charging me, let's say 2%, so I will have to calculate and give you the money back in 5 years at the 2% interest rate. So that's the accumulated value. Also, if we deposit money in the bank at 2%, then the accumulated value is the money we get back 5 years or whatever number of years. R, annual interest rate. N, number of times interest is compounded per year. T, time in years. Before we look at a problem, I would like to mention that there are 2 widely used, famous if you want, exponential functions. 2 famous exponential functions. One is called common, and the other one is called natural. The common one has base 10, and the natural one, does anyone know? Has base E. They're so famous that they have their own key. right here. Yes, I'm going back in a second. So here it is. Here's the key for the exponential with base e, second and e, and second and log. In blue, in my software. In yours might be yellow or something else, some other color. Do we all see the 10 to the x and the e to the x? Okay. Now, because I'm preparing you for the next section, look at these two keys without activating the second. What do they have?
Log
The right.
inverse.
Exactly. They are the inverse functions. Yes. The one with the base e will have the inverse not written as log, but written as ln. What do you think that means? Natural log. And 10 to the x has the key, the same key, shares the same key with log. What do you think that would be? Well, obviously common log. So natural log, common log. Natural exponential function, common exponential function. They share the same key because they are inverses of each other. We'll get to that, back to that. So obviously here, this e is this exponential function. Same a, p, and a, and r and t have the exact same meaning. And now I think we're ready to look at a problem. Let's say 54 on 475. Find the accumulated value of an investment of 5,000 for 10 years at an interest rate of 6.5. If the money is compounded semi-annually, quarterly, monthly, and continuously. Let's go back, read the problem one more time, and establish what is given to us. What do you think 5,000 means?
$5,000 is your principal.
Absolutely. Do you all agree with the principle of 5,000? Okay. What does 10 years represent? Good. Good. What does 6.5 represent, which cannot be used? It has to be 0.065, or indeed the interest rate. What does semi-annually mean?
Twice a year.
Perfect. What does quarterly mean?
4 times a year.
What does monthly mean?
12 times a year.
And this has no n. Continuously means continuously, and we have to use a totally different formula. Everyone with me?
Yes.
And of course, I'm not going to do this by hand. And of course, I'm going to put a formula, which is A equals 5,000, this formula, 5,000, 1 plus R 0.065, X, because I don't have n in the calculator, and the power will be X times 10, or 10X. So what is X? Why am I using X? Because the calculator doesn't have n. You don't have to change the variable. But in the calculator, I will have
But
X.
then we can look up 2 and 4.
4 and 12. Exactly. Excellent. So in y equals, clear. And let's put 5,000. Left parenthesis, 1 plus 0.065 divided by X.
Do you have to do another parenthesis for the 0.065 times X?
No, because it's only, no. It's only because there is one term at the top and one term at the bottom.
Okay.
Yes, I am very, very careful with parentheses myself. So caret, in parentheses, please, 10x.
10 times, or yeah, 10 times.
When we're ready, we will go to second and table. and punch in 2, 4, 12. Go to the right and highlight because you may see a approximation. So I have A of 2 is 9479.19. A of 4, 9527.79. 9527.79. A of 12, say it again. 9560.92.
At least that's what I write down, so she's not.
Are we okay?
Yeah.
Everyone got the same thing?
Yes.
Yes, everyone?
Yes.
Okay, so now we also want the continuous. Continuous is this formula. So then we have I just realized. I'm sorry, this is the accumulated value and this is the principal. That's how I wrote it, but not on the formula. I'm so sorry. Of course, the accumulated value is outside and principal is inside, exactly how we put it in the formula, but I wrote it reversed here by mistake. My apologies. Sorry. 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 Of course. This is the accumulated value. My apologies. We put it correct in the formula, but I just realized that I wrote it backwards here. So one more time, this is the accumulated value and this is the principal. Accumulated value and principal. Sorry about that. My apologies. Okay, so now the accumulate, that's why it's A, right? So 5,000 E to 0.065 multiplied by 10. Since this is just one calculation, we can just do it without using y equals. So 5,000 E, careful how you get the E right here, second and E, in parentheses, 0.065, or you just multiply and press enter. And we get 9577.70. Any questions? Any questions?
That's for the
Continuous compounded interest, yes.
So after that,
That's it. We're done with the question.
what's the formula there?
Yes, my apologies.
Yes, this is the
Of course, that's the accumulated value and that's the principal. Exactly how we wrote it here. I just realized that.
It doesn't have an end to it.
Very good. Any questions? So we looked at two interesting applications with exponential functions. One, that was a model about radioactive substance. The second model was calculating the accumulated value X number of years after we deposit or after we borrow money. And both of them involved exponential functions. As you see, this is a typical combination. You can say, well, we also have a variable here. True, but basically the variable is time or number of compound interest in this case. So it's an exponential function, combination. Okay, let's look at 4.2, which is log functions. We know the two graphs. The notation, we're going to go to the graphs again, but the notation here is, I wouldn't say necessarily interesting, but unusual. Let's put it this way. The base of the log function is still a. It still has the exact same properties, or two possibilities if you want, like the base of the exponential function, identical situation, either greater than 1 or between 0 and 1. And here's the notation for the log. So let's say the base is 2. F of x log base 2 of x. One more time. Log base 2 of x. This is how we read it. Log base 2 of x. Also, we know there are two special log functions. Special log functions. We just looked at those two keys in the graphing calculator. One of them is log, so log x. And the other one is lnx. Of course, this one is the common, and this is the natural. So if you see log with no base, what will you immediately assume? That the base is? Yes. It has to be assumed right away that the base is 10. If we don't see any base, but we see ln, immediately we must assume that the base is, look at the key. Say it again. Look at the keys on the calculator.
EX or E?
Very good. So when we see log, it's common log base. Yes, Priscilla? Log base 2 of x. How we read this? Log base 2 of x. Log base 2 of x. So log means base 10, but we don't write it. It's like with the square root. We know it's there, but we don't write the index 2. The same thing here. When we see ln, we know the base is e, but we don't write it. That's the convention. Okay, so let's look at the two log functions that we already graphed a few minutes ago. Here's one. And this is log base 2 of x. And there was one more. Do you remember what the other function was? We graphed 1/2 to the x. And we graphed this function as its inverse. This was log base 1/2 of x. If you remember the base, when the base is greater than 1, the function will be increasing, and so is the inverse. When the base is less than 1, the function will be decreasing. Any questions on this? Let's refresh our memory. What is the domain of a log function? Pure log. If you look at these two graphs, you will identify the domain right away, in case you forgot. Say it again. Okay, let's look at the graphs. What is the 0 to infinity, as we discussed? The log function is not a friendly function. It's not defined everywhere. It joins the square root and the rational function. It's a function with restrictions. It's a function with restrictions, and we have to be very careful about it. Okay. So when it comes to discussing logs and exponentials, I always consider that the most important concept in this entire chapter, chapter 4, is the following. Very, very important concept. Any log equation can be replaced by an exponential equation and vice versa. I have not shown you how the exponential and the log work together. I have not. I need this concept first in order to show you what's happening here. So this is in plain English, right? Any log equation can be replaced or is equivalent to or can be replaced by an exponential equation and vice versa. Any exponential can be replaced by a log. But how does this look in mathematical terms? Log base a of x is y. So this is a log equation. Log base a of x is a number, y. I wrote a log equation. Then I will present what is called the double equivalency symbol. What does this mean? It means that from the log equation I can write an exponential, and from the exponential I can write a log. It goes both ways. And now be very careful the mechanism. That's extremely important. Base raised to this number equals this number. A raised to y equals x. This, I claim, is the most important concept in this chapter. A lot will depend on it. So, please give me an exponential function, f of x. Any exponential function you want to work with for the next, 2 minutes. A simple one. 2 raised to x. Good. Give me 3 numbers in this bubble. And let's say one of them is 0. -3 and 4. Excellent. Can anyone give us those corresponding numbers for this function? In other words, 2 raised to -3 will be y equals
1/8.
Excellent. Y equals
1.
Excellent. Y equals
16.
Excellent.
We really wrote it.
That's fine. That's no. I want you to check. Don't trust anything. So now I claim that the inverse function is, what is my claim? Help me with my claim. My claim is that the inverse function is log base 2 of x. In order for me to convince you or show you that I'm right, I have to show you that log base 2 of 1/8 eventually will be -3. I have to show you the log base 2 of 1 is eventually
0.
and I have to show you the log base 2 of 16 is eventually 4. Here's how I show you, and then I'll stop. I have 1 minute.
I wrote that very wrong.
So this is an unknown number, but I know that this is equivalent to 2 raised to this number equals 1/8. What could that number be?
3.
It cannot be 3, but it must be. So then this is -3. So I hope I convinced you that log applied to 1/8 would return -3.
So we can't do that.
Yeah.
No.
Oh, okay.
That's what I was thinking about.
No. You're smarter
We
than
were
that.
hopeful.
Okay, so now this is a question. This is equivalent to, can anyone tell us what to write? 2 raised to whatever equals 1. What could this number be?
0.
It must be 0. So then when we apply log base 2 to 1, what do we get back? Yes, finally, I'm applying it to 16, but I know that this is a log equation that can be changed into an exponential. 2 raised to whatever equals,
16.
what the whatever could be? 4. So then I hope you're convinced that this is indeed the inverse function of 2 to the x. Thank you for your patience.